Final talk for today, and it's a great pleasure to say hi to Bas Spitters. This is a Danish initiative, so before it was said we're not very diverse, and I just looked at the speakers list, but I have to actually mention that we're actually very diverse in some other fashion. There's not a single Danish speaker amongst them. So, well, welcome, Bas. You've been your background is very interestingly in pure type theory, constructive logic, including some very recent developments in type theory in general. But you're also Chief Science Officer for Formal Verification on the Concordium project. Welcome.
Thank you. I'm one of the Chief Scientific Advisors for Concordium. There are four of us. So it's Jesper Busch, Niels, Claudio Orlandi, and Ivan Damgaard are the cryptographers. And I'm the one doing the formal verification and smart contracts. So I want to give you a general overview of the Concordium project. This project, I've been involved in this as a consultant for about a year now, and we've in the beginning of the year we've actually opened a big blockchain research center. It's about the university got a grant from the foundation of about 8 million euros over 5 years. So what we've done is we're rethinking the whole protocol stack. So the last two talks we heard were companies looking specifically at verification, and this project is much more like the talks that we heard before from Manuel and from Michel. So we're building a quite similar blockchain. So we're rethinking the whole protocol stack, and we're doing this all via the scientific method. So we're publishing papers about what we're doing. And we're trying to get this adopted as soon as possible. This was also emphasized before. So, and we're actually already within the short time that we've been working on this, we've had lots of innovations at all the levels. So at the peer-to-peer layer, there's more intelligent meshing. We've also moved from SSL to the noise protocol. That's a simpler protocol, and that one actually has been formally verified in the ProVerif tool. There's incentivization going on at this level. That means that depending on the you will be rewarded for behaving well in this at this protocol level. And this has been running. The testnet has been running since November. We're very much in the Danish tradition, so all our protocols have Danish names. So our consensus protocol is called Consensus. This is a proof of stake with delegation. Our consensus protocol basically has all the features that were presented this morning by Mikali. On top of this, it also has, well, the important thing is it's already running. On top of this, we also have private proof of stake. There's a paper that's published about this. We have maybe one of the most advanced finalization layers, and we've started to actually verify this protocol. So we've implemented much of the protocol in Coq and extracted it to Haskell, and then an optimized version of this is actually running. But I'll get back to that formal verification aspect soon enough. You can read all about both the private proof of stake and the finalization layer. So those two papers are out at the moment. Then, so as I emphasized before, what is very important in Concordium, this is driven from the business side. And the big issues to solve there is compliance. So we want to have KYC and AML. And this is a main reason to start yet another blockchain, because we're the first blockchain in the world that actually does this properly. And we've been looking very carefully at the regulations, so what's needed for this, and then translate these questions from the regulators into cryptography. And there are a number of papers coming out. Ivan Damgaard, he presented this 2 weeks ago when we had a big a scientific blockchain meeting in Aarhus. The way it works is that so everyone gets an identity, which you get in an ordinary way. You use your identity card. You go to an identity provider. This could be either your government or a bank, and then by zero knowledge proofs, you keep control of your privacy. So all your transactions are private. So this is different from Bitcoin, which is basically Twitter. You actually have everything. You only have pseudonymity, but all the information, once this pseudonymity is, once you know how to link the hash to the actual person, everything is in the open. So that's not the model you want. On the other hand, there are other projects which are completely anonymous, and that also gives problems with people doing really illegal stuff. So that's also something we want to avoid. We want to have something that actually fits in the society that we currently have. And we're doing this with world-class cryptographers, and this is actually running already on the chain. And we're the first to have this. Then the scheduler, so the talk before by Banyo was very important. So we're using accounts in part because this is easier to explain to regulators. On the other hand, there's a translation between accounts and UTXO, so you can actually go back and forth. So in some way it's a choice. The way we're thinking about this is the Acorn model, so it's message passing instead of having a shared state. So this is maybe a more modern way of thinking about this, not thinking about this as object-oriented, but as Acorn model, and message passing. Like the other projects, we also have contracts as pure functions, and I think this has already been very well motivated, that this is a very clear direction for third-generation blockchains. Because we have contracts as pure functions, there's a lot of opportunity to actually parallelize a lot of the execution. So we're working on this. We have a high-level smart contract language, and as I said before, one of the benefits of this is that we can actually rethink what we want these languages to look like. What we have selected is a language from the ML family. The ML family is famously, it has a very precise semantics. So it's a family of functional languages with a very precise semantics. And so we've chosen Elm because this is a very friendly language. The infrastructure around it gives very good error messages. And it's in some way a functional version of JavaScript, if you want. It's very easy to write these contracts, to write programs in Elm, and its simplicity is also one of the reasons why we chose this language. So Elm is still fairly complex. What we've done is fix the number of runtime exceptions that were there in Elm. So this is really improved. So it's really an improvement of Elm. There's a low-level language because so we have more freedom. So we have some kind of virtual machine, which is called Acorn. There are language-level crypto primitives, which we've added to Elm. And then we have communication between contracts. We have programmable accounts, so you can actually have your bank account do things for you. I won't say too much about this now. And this is what I already said. So all your transactions are actually private, and this is guaranteed by cryptography, and it's fully AML and KYC compliant. So this is very important for the adoption. Then there's so here's the scheme to actually motivate people to work so that this is the tokenomics. So this is designed to support growth. And as you can see, there's a lot of interaction going on here. So the foundation for instance, provides wallets to the users. The identity issuers, they provide identity to the users. The users can delegate their stake, and users can use smart contracts from several developers. And together with people at ETH, these are economists. They actually worked out all the reward structures so that this actually works. And this is based on the idea of having a central bank, and this will be controlled democratically. It's a bit more here. Here's the timeline for where we are. So we'll soon have a public beta release after the summer. Then a launch of the release candidates, and then the tokens will come after that. This is the setup of the. So there's the Concordium Foundation, which is in Switzerland, and then we have in Denmark we have the big research center, and we also have the R&D going on here in Denmark. And there's a development office in Spain. All the IP that we generate from the university will be owned by the university, and all the other IP will be owned by the foundation. So there's a lot of, and all of this will be, so all the IP that comes from the university will be completely open. I think I've announced this already. Yes. So we're very much a third generation blockchain. So it's science based. A lot of things, a lot of our results have actually been published already. But one of the things where we're actually very quick is from the basic science to actually having running code. And this has been done within 12 months, really from the conception of the IDs to now having a running testnet. So here are some of the places where we look for applications. So both in governments and NGOs, financial industry and automotive. So I found it very interesting that we had this talk about applications to automotive. So now I want to shift a bit from, so this was to give you a bit of the general context of, this is a bit bigger than I thought, to give you a bit of the general context of the Concordium project. So now I want to talk a bit about formal verification. The nice thing is that this has already been very well set up in the previous talk, so I can probably go a bit faster. So in general, blockchains provide trust, so this is done by decentralization, security cryptography, open implementation, scientific reviewing, mathematical proofs, and formal verification. Now what we do is we translate, if we look at the formal verification of elliptic curve cryptography, so I think some of the previous talks, they have focused on verifying programming languages. Now I want to say a bit about what we're actually, so we're looking at verifying the whole stack, at least as an ideal. So we started a collaboration with Diego Arana. He's part of the blockchain center, and he's an expert on the implementation, a very fast implementation of elliptic curves. We have a joint PhD student working on this. And what we're doing is looking at a number of elliptic curves. So as you probably know, elliptic curves is one of the bases of modern cryptography. Here's an artist impression of an elliptic curve. And what we want to do is to translate these elliptic curves all the way down to logic. And we want to, we need to get the computer to be at the level of advanced bachelor courses, either in mathematics or in computer science. But then once we have built up all that mathematics, we need to refine or compile it to efficient and secure implementation. There's a bit more about, so what we've seen today is also in the first talk, there was a claim proof that the consensus algorithm was correct. So cryptographers often provide mathematical proofs, but the proofs are hard and not always complete. I'll have an example in a minute. And what is nice is that, I mean, we're computer scientists, computers can actually help to fill in these details. And we can see an emerging field of computer-aided cryptography, but this is really slow progress. So, but this combines cryptography, programming language, and formal verification. Because there was some reservation in the beginning, so would it actually be a good use of our time to verify a whole blockchain stack? I'd like to compare to what was the state of the art in TLS not so very long ago. So as you can see, TLS was riddled with bugs, and so this was extremely dramatic. So we had Heartbleed, for instance, which would allow anyone to read all the traffic you were sending. So then there was a big effort by a number of parties, but I think the joint Microsoft INRIA project, they put on a lot of people to actually work on this. And what we now have is both a new TLS standard, so this was done, of course, in general work in the TLS committee, but also a completely verified implementation of TLS. So this is now the new standard. If you're using either the Firefox browser or the Chrome browser, you're using a verified implementation of this protocol. And of course, there's still, so what we've heard a number of times before, the specification here is extremely important. And of course, there's a very precise specification of what has been proven correct and in which precise attacker model. So these kind of things, it's also very important to make these specifications public. This is something we're building on. So Concordium uses both the Hackle library and Fiat Crypto in various places in the code, and we're building on top of these libraries. We've heard the TheDAO problem before. This is a picture of what a, can I point? Yeah, a picture of the stack of what a blockchain looks like. And we've had the horrible accidents with the DAO, but also a recent problem in Zcash. This is anonymous cash, and they're world-class cryptographers. And what they did was to do precisely what I was suggesting. They published a paper. There was a follow-up paper, which again was published, was refereed. Still, there was a bug in their code, and it really allowed people to print money. So how could this happen? Well, this was very carefully refereed, but there was basically an off-by-one error in the protocol. So just doing the standard refereeing process in cryptography is not good enough. We actually need to do a verification of the cryptography in a proof assistant, and then make sure that we generate the code from this, because we need to know that there are no bugs in the mathematical papers, in the cryptographic papers, but also to know that the code is running is connected to the protocol that we've specified. Now to give you some challenges of why this is actually difficult. So the standard reasoning about functional programs, or maybe imperative programs, that's quite well understood. There's a verified C compiler, for instance, that is very well understood. There's a verified microkernel. Some new challenges in the blockchain space is that we need to reason about probabilities. This is hard. Distributed systems, that's also a new challenge, and adversaries. The nice thing is that there are all kinds of nice parallels between what the cryptographers have been doing and what's been happening in the programming language field. So there's a nice interaction there between those two fields. But there's a lot of active research that needs to be done there. So what we've started to do is to actually, there's a paper proof that the consensus comes with a composable proof of security. This is a precise notion in cryptography. That means that the protocol is not only safe by itself, but also safe in any environment you put it in. And this is something that cryptographers care a lot about. What we've verified is a key fragment of this protocol in the COC proof assistant. The COC proof assistant is the state-of-the-art industry strength proof assistant, which has a very small trusted code base. So within type theory, this is probably one of the most mature proof assistants. It's been going for, I think, 25 years now. And they got an ACM award. So what we now have is a formal connection between the paper protocol and the running code in Haskell, and we're refining this into an efficient implementation. And I believe that this is the direction to go into. So I'm also quite excited by your work in this direction. I think we've had this. So the third generation, so we have the luxury to start from a newly designed programming language. We don't need to verify solidity, for example, but we can actually develop our own programming language. And what you can see in this third generation of blockchains, there's a focus on language with a functional core. So there's simplicity that has been around for quite a while. That's targeting blockchain, actually. There's the liquidity of Tezos, there's Plutus by Cardano, there's Scylla from the Silica project, and we have Oak, which is also a functional smart contract language. So this has many advantages because it's easy to think about, and there are also lots of programming advantages, but we've heard this a couple of times before. So what we're building is a framework for verifying these smart contracts. What we've done is embed the Oak language in COC and prove properties, for instance, about the crowdfunding project. And there's some new challenges in expressing functional language in a proof assistant, which we've addressed. And we've also made a provably correct implementation of the Congress. Congress is basically the essence of the DAO. So we specified what the DAO should actually do, and we've proved that our implementation of the Congress in Oak actually does that. As a very important part of this is we do not only need to verify the programming language itself, but also the execution model. And this is how the Congress or the DAO is actually different from lots of other reasoning about programs. We actually need to look at the communication between the different contracts. So there's some interesting new challenges here. So I just wanted to show you this, is that there are many interesting challenges in the design of safe blockchains, and we're using computer-aided cryptography and modern smart contracts design. The nice thing about these new smart contracts is that they have a clear semantics and are easy to analyze. The company is hiring people, and we also love collaborating in the center. So thank you.
Time for questions.
How hard is this in your experience with specifying something COG, extracting to Haskell and so on, to get the kind of efficiency that you need for low-level cryptography in protocols and so on? I mean, there's usually quite a lot of data to handle, and you have to be careful about memory allocation, all these kind of things.
So there are a number of things to say about this. So we needed a new curve. So we spent some time at looking at trying to see how to implement it ourselves. Then we looked at fiat crypto. This is this framework developed at MIT for actually generating these curves. Took them 5 minutes to generate an efficient implementation from just a mathematical formulation. So this is something that's fully verified. It's also known to be constant time, so there are no side channel attacks. So in this case, this has been developed to such an extent that it's actually much better than anything you can do by hand. In other parts, so there's a lot of work going on in also in verifying Haskell, for instance, which you probably know about. They're computing generating something that works okay. That's not too hard. Refining that into a more low-level, efficient implementation, I think that's harder, but that's also where a lot of interesting challenges are. But there's also something that there's a lot of, for instance, there's the big deep spec project where there are 10 American universities that are working very hard on making this more efficient. And for this part of the smart contracts languages, there's a lot of development just in the area that we can hope to profit from. So, and the nice thing about COC, it's used by lots of people, so we can just profit from lots of research that's going on in the area.
So, related question. It sounds like many of these things are original, but some of them are actually not specific to the blockchain. Like so you couldn't just take some things, like the Everest project is not relevant to you somehow, the Microsoft Everest project.
Oh yes, no, I mentioned it actually on the slide. No, that's so we're using Haskell, so we're using Everest in the at the peer-to-peer layer, and we're using fiat crypto for some of the curves we're using. So we're using off-the-shelf technology. So that's the nice thing. But well, obviously, I mean they only did some of the curves, and we need a few more because we have all kinds of innovations at the crypto level. So we need to extend these libraries, and so we have experts involved in doing this. So we're working on off-the-shelf technology.
No, but somehow maybe it's the kind of question, what do you have to do which is specific to the blockchain as opposed to that it's just more efficient? What is actually specific about the blockchain here that requires extra work? It's just
so for cryptographic primitives, I don't think it's too specific. So this will also be we'll release everything in open source, all the contributions we're making there. But, well, as I had on my slides, there are a number of things. There's this unique combination of, well, basically secure distributed systems where you have an adversary, you have probabilistic programming, and you have distributed programming. And that's very hard to reason about. And there's a lot of new technology needed to get the right reasoning principles for these things. And of course, there are more secure distributed systems, but the blockchain is an ideal area to develop these in.
You're working in a domain of KYC and AML, and
yep.
in general, legislation says you have to know your counterparty. So parties have to be authenticated, and I guess the authentication then is not just there's an external service. So in that domain, there's a number of distributed ledger technology platforms offered that then use conventional, Byzantine consensus protocols. Can you say something about the relation to, for example, I don't know, Corda or Hyperledger Fabric, which are quite popular? There are other ones, of course, but just to get a sense of the positioning of Concordium there.
So I think that the big difference is that those are permissioned blockchains, so they would typically be run within a collection of banks, whereas Concordium is permissionless, so it's completely open. And getting all this technology to work in such a completely open setting, so that's one of the contributions here.
So it's similar to some of the other talks we've heard about, proof of stake to make sure it's Sybil resistant.
Yeah, okay. Precisely. Okay. Yes.
How about the smart contract notion? Popular one is that a contract is really a program that manages an account, is a single account, and through that one you can invoke other accounts. Is that also the notion of smart contract in Concordium? A program that manages accounts and provides exclusive access to those accounts?
Yeah, I think the model is quite similar to, well, a number of related projects. So, but we're using the account-based model as opposed to the UTXO. But that's maybe mostly a technological reason for that.
So many of the properties there of interest in verifying, as we've seen, are actually quantitative in nature. So, for example, making sure that if you participate in a congress, it's fair in a quantitative sense. And in the real world, I guess that's also possible to program. You have a lot of different resources. So can you, for example, resources like money and I don't know, bicycles and cryptocurrencies and I don't know, kroner. Is there a way of what do you think about addressing the question of like, is this a fair contract which you can only evaluate once somebody tells you, oh, this is the valuation you should apply to those things too, because it depends on actually how the exchange rates are between those different currencies that you have. Sounds like a technical question, but it has to do with the fact that usually we don't just deal with one piece of money, not just kroner.
Yes.
But we have kroner versus yen and Bitcoin versus bicycles, and so we have lots of different currencies in the real world. And whether something is a fair non-exploitable contract or not depends on what it means to have a house bought for $5, because what is a house?
Yeah, so. That's something we haven't thought about before. I mean, we've been looking at the whole stack, and this is sort of on top of that, I think. Yeah.
Well, other questions?
So you said that you like to see smart contracts as pure functions, and that is beautiful. I just wonder how you deal with contracts where you need to store a large state, like ERC20, for example, right, where you have like these billions of accounts, and each transaction is just a little code that updates a little delta on the big state. So I wonder what your experience with such.
Well, we're using the monadic way of reasoning about state, or in essence, that's what we're doing. So
I'm thinking more of the programming model. So how do programmers deal with that? They just send a normal transfer without worrying about the state? Because when you write that in Solidity, you will match the to account, the from account, right? And you say, I'm modifying the to, and I'm modifying that big vector of balances in two places only. Right? So you have to recode it differently, right? As a pure function. I agree that the verification is easier. I'm just wondering about the programming model. Would it be harder for programmers?
In our experience, this has not been. It has been very pleasant to write contracts in Oak, but I haven't done this comparison yet. So maybe I can come back to you about this. Yeah.
I think this concludes your wonderful talk. Thank you very much, Bas. And it concludes our symposium for today. So I hope you enjoyed it, because we can't change it now. So thank you for coming, and hopefully, as I said, you won't say terrible things about it. Thank you very much.